Okay, thank you everybody and happy Christmas in advance. When we talk about from catchment to rivers, there are some, I would say, some misnomers. Okay, so before I start this topic, let me first introduce you certain terminologies like you may have heard hydrological modeling, hydraulic modeling, and let me also tell that all these terminologies, sometimes they create confusion. What I'm trying to talk here is to introduce to a non-hydrologist how to do the mathematical modeling for the flow which will come from the catchment and will join the river. So this will be my outline of presentation. I'll introduce the hydrologic cycle, which is the most important thing to understand so that one can do the modeling. And then, of course, I'll define catchment, then some modeling concepts and what we need as input data and what we get when we do the modeling, and of course, some critical remarks. This is the hydrological cycle I have copied from this website. As you see, and these days they teach hydrologic cycle even to class 3 students. And it is very, very important in the sense that because of water, life is here in this planet. So we must know something about water. Once I was facing an interview and somebody asked me, what is the first limb of the cycle? And you know, when we say cycle, then we are of the opinion that anything can be the starting point because a cycle is a cycle. But that is not the correct answer. Okay. And my sincere suggestion to all of you to find the answer from any good textbook or maybe in the internet you can search. Anyway, jokes apart. Here, as you see, different hydrological processes, and you can see the arrows. That means, let me start with this process called evaporation. And from the ocean and from different water bodies like river or reservoirs, there will be evaporation. Also, there will be evaporation from the soil, the earth's surface, and there may be evaporation through the plant body. We call it transpiration. And it goes to the atmosphere. And then through different processes like condensation and other processes, there will be formation of precipitation, the clouds, and then precipitation may occur. And as the water goes back, as it comes back to the, again, Earth's surface, it completes a cycle, but there are certain processes. For example, some part may go as runoff, but some part may go as infiltration. It may join the groundwater. The groundwater flow may again either join the ocean or it may move, it may join a river nearby. So in one sense, it is completing the cycle. So we need to understand here that for a given volume of water, the whole thing is being recycled. So there are several studies on this. For example, if you see this picture, it gives some numbers. You can see the numbers in the red color. For example, here it is 40, 413, some numbers here in red color that indicates that what is, if you can just add, I mean, the arrows going up means it is contributing towards the atmosphere, and the arrows coming down give something to the earth. That means we can calculate and see that the conservation principle, conservation of volume, is satisfied. Similarly, you can also see the black numbers like 176. Those are the total storages. These numbers are units, and one can see this reference to find out in details regarding the numbers. But the point I am trying to mention here is that the total volume of water a kind of constant. So the interplay between these physical processes, these hydrological processes, they are into the play, and then this hydrological cycle is conducted. One most important thing to remember here is that there is transportation, meaning something is being transported, and there is also the play of phase, meaning it may be in gas form, water may be in liquid form or in ice form. So these two important aspects are there with the hydrologic cycle. With this basic information on hydrologic cycle, now we'll see how we can do the modeling. Before that, why to do a hydrologic modeling? And some other synonyms for hydrologic modeling is sometimes we see, catchment modeling, watershed modeling. There are some similar kind of terminologies. So, as I said in the beginning, water is the main life force in this planet. We must know something about its use, its behavior, its play or interplay between the processes. So, in view of that, whether it is water resources planning or management or design of hydraulic structure or transport of pollution in a river, or for that matter, water supply to a city, you take any aspect of our life related to water, we may have to do some kind of hydrologic modeling. By the way, let me here also clear the thing that when we say hydraulic modeling, it is slightly different in the sense that hydrologic modeling is the modeling part in which we bring the water from the catchment. I'll define what is catchment, from the catchment to the river. And when we say hydraulic modeling, that means in the river, how the water propagates. So this talk is exclusively on hydrologic modeling. I am not covering hydraulic modeling. When we say modeling, there are n number of models. For example, if I say rainfall runoff modeling, without doing any kind of equations, I can do the modeling. How? I can just use, of course, that will again be counted, that may be counted as an equation. I may just consider that depending on this surface, maybe let's say I am doing the runoff calculation for my campus. So I may just consider, oh, this campus is this much of water, this much of roads, buildings, or garden, and I may consider a factor something like 80%. So if there is an event of rainfall, maybe 80% of the rainfall will be towards runoff. So that kind of a modeling is also available. So this modeling, this word modeling, we should not be misguided by that. What essentially we mean is that a physical process is there in place. It may be a chemical process or a biological process, but a process, we try to understand the process, or we try to simulate the process by using some kind of mathematical equations. So we may use a very simple equation to describe the process. We may use a complicated partial differential equation system of equations, or for that matter, when we say there is an experimental model, let's say, okay. So we should not confuse with that. Here, essentially, we the importance is how we can do the mathematical modeling. So essentially, by using some computer program or by using some software, that kind of a thing. So there are, in hydrological modeling, there are different approaches like black box model or lump model or distributed model. So one has to know little bit about these models. And before we attempt to use the software, because when there are so many softwares and many softwares are freely available, why should we go for writing our own code? Of course, many people prefer their own code because you have a complete control over the code. But assuming that we are going to use some software, then we must know these because the software may have different models. We should know before using the software what are these models. So in hydrologic model, as I mentioned here, there are several models. One should know about these models. Okay. And again, this empirical model. So there may be sitting somewhere, or if you find in the literature, there may be some relationship, and then you are excited to use that. So it is good if we use empirical model, but at the same time, we should be very clear what are the assumptions used in this, or where it has been developed, because this hydrology is a very, it is global as well as regional. The regional hydrology is extremely important. If some empirical equation is developed, let's say for some particular basin in India, then if somebody is using it for another river basin, he has to be careful. Maybe the model parameters has to be revised. This is a catchment. On the right hand side, the red line indicates the boundary of the catchment. Other words for catchment, there are several words like some watershed, somewhere I read divide, and the most important thing is that if there is an event of rainfall in this boundary or inside the boundary, then it is contributing towards the outlet. The most important thing to remember for a catchment is that the outlet is through a single point. So if I am considering, for example, once again, a city, okay, or maybe my campus, and suppose there are 5 different exit points where water is going out, then if I consider the campus boundary to be the catchment, there is a problem. Because when I define the catchment, essentially the outlet point is to be just through one point. So water may come through these several locations, as these blue lines indicate. Water may travel through different paths, but essentially they have to go through that single point of exit. And if raindrop occurs outside this red line, it will not come into the catchment. So catchment is defined by this. That means if the contribution by the rainfall is, this outlet is being contributed by this area, that area defines the catchment. So if we use a common sense, that means we have to use the topography, meaning the elevations of the place, to find out what is the catchment. Because when I do the analysis for a river, whether it is for constructing a bridge or to do some kind of modeling for my city, or whatever water analysis I do, it is important to first find out what is the catchment, or what is the area that is contributing water to this location. So in view of that, we must use a elevation model, or popularly called as DEM, as they call, digital elevation model, meaning for different coordinates, different XY values, you have the Z value, meaning the elevation value, and using that information, you can prepare the elevation model, meaning you know the topography. That will give you the idea where the water will flow, because water flow follows a very simple principle, that from higher energy to lower energy it will flow. So elevation data is extremely important for hydrologic model. When I say catchment, I can consider the catchment as a whole unit, but at the same time, as I said, there are different modeling approaches. Usually what is done is we divide the catchment into different sub-units, and these sub-units are called hydrologic response units, HRU. As you will see in different softwares, so you have to give the information for the catchment through these HRUs. So the user is to define what is the HRU. So you may have to, for example, you can see the figure here on the right hand side. This is the catchment, the outside boundary, but then the catchment is divided into different sub catchments, HRUs. So that is again up to the user. Of course, if you use these softwares, they help you a lot, but you should have some idea, because you have to have some familiarity with the locality, so that you can know where I should use, which area I should use as a sub catchment. So for the purpose of modeling, these sub-catchments, they are the cells or the units. Okay. Again, each sub-catchment may be divided into certain grids to help us in the mathematical modeling. All hydrological models, they use a simple principle of conservation of water volume. So many people, they consider, usually in a typical water resources group, there will be people working in hydrology and in hydraulics, and often they fight, of course, friendly fights. And they say, oh, you hydrologists, you don't know anything. This is like chemistry because you use simple equations. But friends, please note that, by the way, I am a hydraulics. Please note, although the principles are very simple, these are extremely useful formulations. For example, all hydrological models, they use this simple principle of water budget equation, meaning that the total volume of water is conserved. There are sophistications and more revision to this, but let us go with this simple equation. For example, on the left-hand side, this is P is precipitation or rainfall. This is the inflow or the discharge which is coming to the watershed or catchment, and ET is evapotranspiration, and delta S is the storage or the change in storage. You can consider everything in terms of volume. Sometimes you may also see some texts used in terms of height. For example, precipitation may be used in terms of height, not in volume. So this equation can be used. It is up to you. You decide whether you will use volume or height. But the principle is that total water volume has to be conserved. So total inflow minus total outflow should be the rate of change in volume. That is the thing. So we may have to use some measured parameters like measured precipitation, or sometimes the discharge, measured discharge. Sometimes we may have to fit the parameter to some given data. Sometimes we simulate the parameter. So one has to be very, very careful when you use the input into your model, or when you get the output. You must understand what is this, whether this is measured or fitted or simulated or what. These are these different inputs to a typical hydrological model. Digital elevation model, as I discussed a few minutes back, and land use, land cover, which essentially says you that this is the use of the surface. If it is a road, water cannot pierce through the road. If it is a building, this is again, it will check water. If it is, let's say, loose soil, water will go into the groundwater through that. So land use, land cover map is very essential for hydrological modeling. These are the inputs used. Similarly, soil type and weather data, essentially precipitation or wind velocity, temperature. So if you have remembered what I discussed in the hydrologic cycle, to assess different components of the hydrologic cycle, we need this information. And again, I repeat, there may be a very simple model for any component. There may be a complicated model. There are several models. So one has to use appropriately depending on what is the purpose. You can choose whatever model you want to assess or to estimate different components or the water volume due to these different hydrologic cycles. So this is a kind of flowchart. This is not the only flowchart. It can be done in several ways, but this is just a representative of a hydrologic modeling. So this is precipitation, which is coming in, and interception means the storage, or if there is a pond or depression, the water will be captured there. So that is interception. And then there may be surface storage. So this ET is evapotranspiration. So different processes are there. These arrows indicate how the thing is moving, how the thing is sequentially progressing. And depending on that, finally, we find out what is the channel flow, or what is from the catchment, what amount of water, because of different hydrological processes, there will be several losses, but then there will be something which will contribute towards the river. And if you have remembered that small figure from the sub units, so let me go back to that. From these sub units, for example, from this sub unit, first this sub unit will be calculated what will be the runoff in this. That runoff will come to, depending on the topography, will come to another sub unit, and in that way, from the entire catchment, we consider small units. From each individual sub units, the runoff will be finally contributed towards the river. So it is a question of time also, meaning with time the process will progress. This is sometimes called a marching thing. So we march the problem, and then we see what is the outflow in the catchment. So this is the sequence usually we use in hydrological modeling. We first choose the input data. You may have to do a lot of exercise to collect the data. You may have to go to that office, this office. These days, it is a good thing that many of these data are available in the net. So for example, the rainfall usually is available. Then evaluate the study objectives under various watershed conditions. And usually I suggest whether you are doing your PhD or you are doing a project for the company, or you are doing, like a research project, depending on your objective, you decide what kind of modeling aspect you are going to use. And of course, these days fast computers are there. So usually computational facility is not a constant. Few years back, 10 years back, it was a constant, but these days these computers are too good. And selection of methods for obtaining basin hydrographs and channel routing, calibration and verification of model. This is extremely important. You may have a model, and today's models, they are, even if you don't use any data, they will run. They will give you some number and colorful graphs. So you may be very happy because it is being computed by the computer. So how a computer can do error? That is not correct. So this calibration process here is extremely important. If you have some observation data, you must compare your results from the model with the observed data. That way you can know, you can fine tune the model parameters, so-called model parameters. The model simulation then once your model is ready, now you can use your model to simulate different conditions. You can play with the catchment. Please note that a river, a stream is not those just two banks. It is the entire catchment. So if you are doing some kind of activities in some part, if you are developing a town, or if you are disposing something somewhere, it will affect any activity in the catchment. Is again, it is going to affect the river. So one must use different simulations. So that way you can suggest to the authorities what they should do, what they should not do. And this is also one way, a sensitivity analysis. And then of course evaluate usefulness of model and comment on needed changes. So these are some figures from the, for example, this is the land use, land cover. The left hand side is for Musi river. Currently we are doing something for Musi. So this is the different colors, and different colors indicate, I have not indicated, you can see this figure for the colors. So that gives you the idea about land use and land cover. And in these kind of things, if your study area is small, for example, if it is a town, it is not a bad idea to have a field visit to see the place for yourself. This is the elevation model. For example, different colors indicate different heights or elevations. I have not given the colors, but it is again for Musi. And similarly, this is the soil type map. The entire area is primarily by this blue kind of these numbers. They indicate certain kind of soils. So there is a one-to-one mapping, meaning color or this number, and what is the soil type, like sandy soil or loamy soil or sandy silt, like that. So different kinds of soils here, as you can see, primarily it is this blue, which is governing the whole of the catchment, Musi catchment, and then little bit of green and gray and pink. This is a typical result. Usually we try to find out the hydrograph, discharge hydrograph. There is something also called the stage hydrograph. usually from the hydrological models, we don't get the stage hydrograph, meaning the water level versus time. This is time, x-axis is time and y-axis is discharge. And as indicated, the dashed red line is the observed and the blue line is the simulated. So you can fine tune your model parameters so that suppose your interest is to match the peak values. So then you can play with the parameters so that the peaks are matched. So depending on your objectives, you can go ahead with that. So I'll just conclude here by saying these critical remarks. For example, I have written 16 by 64. We all know the answer. The answer is 1 by 4. But one may use the logic that I cancel 6 and 6 from up and down. We all know that that is not a correct logic. So when you are using a computer program, you should know the logic, what is inside, and you should not use this as a black box model. So without understanding the physics, it is true that you are not writing the code, but at the same time, you should know a little bit what is it doing, what the model is doing inside. So that one should know. This is garbage in and garbage out. One must know the correct interpretation of the input values and similarly the output values. I have known many examples in India. At least I can cite 10 examples, which is CAD. We think CAD is computer-aided design. This is computer-aided disaster. So when you do a design, and I was talking those 10 numbers as for bridge design, the bridge collapsed. Why? Because those are designed by computers. Okay. So when it is computer-aided design, it should not be computer-aided disaster. You must interpret your outputs in a very, very positive way, and you should understand what is there. So there comes the role of, otherwise software is there, anybody can use it. So there comes the role of your knowledge base. And regional hydrology, I keep on saying this because we see many formulas, many things, this method, that method, this model. But regional hydrology is extremely important. If you are doing some analysis for some region, you must take into account the regional hydrology. You cannot just rely on a global model. Global models are good. You use the global model, find some results, and then fine-tune the results using regional hydrology. And that includes also calibration. What I said, calibration in my discussion, calibration is equally important. I will stop here. I know that I just talked on the periphery, but at the same time, I would like you to ask some questions if you have. You can unmute yourself and then ask me some questions.
Thank you very much, Pranab, for this overview of watershed modeling for people who are not so familiar with this area. I feel a little bit bad that I didn't explain at the beginning why we are having this in this session, to highlight the importance of this modeling for the transport of antimicrobial resistance. So if you imagine that the rainfall runoff might be carrying fecal material from animals or livestock, and the rivers have inputs of sewage that are then transported with the rivers. This modeling enables us to understand how much the material that enters the rivers is diluted, how much the material is, how far the material is transported, and where it ends up. So you have to imagine that in this water cycle that Pranab has shown at the beginning, the water flow is going to transport bacteria, whether they are resistant or sensitive to antibiotics, and it will transport chemicals and it will transport nutrients for the bacteria, whether they come from sewage or other sources. So this is really about transport of material through the environment, and that is why I'm very pleased, Pranab, that you gave this introduction for everyone into this watershed modeling, the hydraulic cycle.
Yes, let me also tell you that this hydrologic cycle that I showed is a general one, but for a city, in an urban environment, the hydrologic cycle is slightly different. So the purpose is when you do the hydrologic modeling, then you can know which component is contributing in what way, and accordingly you can use your policies, you can revise your policies.
You can type any questions into the chat or just unmute yourself and ask questions. Please go ahead.
Hello, Dr. Pannam.
Yes, yes.
Thank you very much for delivering very nice talk. And it is the topic is new for me, but I enjoyed this is the first lecture, so I have not escaped any slide. So can you explain that what is the role of your regional hydrology in studying the contamination flow or microbial flow from the upper aquifer to the lower aquifer?
No, it is not that way. When I say regional hydrology, that means suppose there exists a global model. Let's say y is equal to ax. This is a hypothetical model. So this A may have been developed by somebody in US, let's say. And for that particular catchment, A may be different. But when I am using this equation in Hyderabad, I have to be very clear what will be the A value. That may not be available in the literature. But at the same time, I should examine this existing relationship, and I can come up with what might be the value of A for my region. So when I say regional hydrology, the meaning is that.
Okay, that's fine. That's fine. Thank you.
Hi, it's Liz Wellington here. Hi, Bernard. That was very, very nice. And it reminds me a bit of some of the work we've done with engineers in Warwick University, where I'm based. So one of the things we're thinking about with the ARG and transport of bacteria is the deposition rate. So you have downward movement in your model as well as lateral flow. And is it reasonably straightforward to incorporate particulate matter and look at how the relationship between flow rate and deposition, because a lot of the genes and the bacteria are in the sediments when we sample, but obviously changes in flow rates and everything. So I'm very interested in the relationship between sort of wet and dry season models, and also, the extent of clear out of sediment. I don't have any real feel for that. Obviously, there's quite a lot in the literature, but sedimentation is quite difficult. And now we have the plastic particles. In most rivers, there's a lot of plastic, and the level of colonization of those particles is really significant in some cases, depending on the transit time in the river. So these are things I think where the bacteria are going to be associated with. So that I was wondering about that aspect.
Yes. Let me tell you two different aspects. When it comes to sediment, there is sediment transport from the catchment. When rainfall occurs, through that rainwater flow, some sediment from the basin, from the catchment comes and joins the river. That is one aspect of sediment transport. But then there is in the river itself, there may be sediment transport. It may come from the upper side of the river or from the river bed itself. It may come, and eventually it may be, getting deposited at some place. So when it comes to hydrological modeling, some models are equipped with estimating the sediment from the catchment. So it is there. Some modules are there. One can use those modules to estimate what is the sediment coming from the catchment and joining the river. And when it comes to sediment transport in the rivers, one has to use hydraulic modeling, not hydrological modeling. And this bacteria growth and all those things, those are to be coupled with these hydrological modeling kind of a thing. So the output from the hydrological modeling will be treated as input to a bacteria growth model. And currently we are working on that aspect. To my knowledge, no model exists like that. I mean, which can take care of both the things. So we are kind of trying to develop this model.
I'm pleased you say that, because I thought I might have missed something in the literature. I was looking and couldn't find too much. The things seem to run a little bit in parallel. So I think that's something that this may be a really important output for our projects. Because I think this is really something critical.
Yeah.
Thank you very much.
Thank you.
Please do feel free to ask any questions about aspects of the talk that you didn't quite understand. That is the purpose of the workshop, is really for you to learn about things that you are not working with on a daily basis, and an opportunity to learn a few different things.
I have a very basic question.
Yes.
How long does it take you to get all this data and build a model? Like,
so this is interesting. It actually depends on you. For example, if some student is already working on some basin, he or she may have already the data. So the next student can use his or her data. So for example, in case of our project, the Musi River, we are under some data are already available through the internet, but some data like the reservoir releases and the releases from the nearby nalas, those data are not available. So this is a tedious process. Data collection is a tedious process. When it comes to running the model, this is pretty straightforward. If somebody has, even if somebody has not done a course in hydrological model, still he or she can use the hydrological model, and these are very user friendly. Some basic concepts are to be learned, and then it takes something like I would rather give 2 days to 7 days, something like that, to understand the entire how to build the model, how to run the model, how to calibrate the model. To learn all these things, 1 week is more than enough. And once your model is ready, now all set to go. And it doesn't take, these kind of models does not, they do not take much time. Your computational time is very less. Something like, if it is a very huge catchment, it may take something like 5-6 hours. Otherwise it is below 10 minutes. And again, what period you are trying to simulate? Let's say you are simulating the flood for last 50 years, then it will of course take some time. For a problem like this, usually, of course, doctors differ. Many people argue that one should use the entire period, like 1950 to 2021. Why not? Data available, you go with that, run it. But then I have a different suggestion. Usually what I do is I identify the critical floods. So if you look back into the history or newspapers, they will always indicate you that yes, in maybe 1995 there was a very significant amount of flood. So you pick up those 6-7 events and try to simulate that. If you are doing that way, each event will not be for more than 7 days. So you are essentially simulating an event for 7 days, which will be like 10 minutes, 20 minutes, not more than that.
Anna,
yes.
Maybe you could comment a bit on the differences between dry and monsoon season in India, and how much of a difference that is, or from your point of view, how it affects the modeling.
Can you please repeat difference between what?
Between the dry and monsoon seasons in India, how much of a difference is this for us in the UK who are not haven't got that experience as much?
Okay, I'll come to this aspect, and I'm not sure if I have understood the question, but let me bring here a very interesting aspect of the modeling. For example, in the current project, we are dealing with two different rivers. One river in Chennai, the other river is in Hyderabad. The river in Chennai, that is primarily rain driven. If there is an event of rainfall, there will be heavy amount of water in the river. So we are trying to simulate that. On the other hand, the river in the Hyderabad, Musi River, it is primarily driven by the releases from the reservoirs. So throughout the year, it runs dry. And what is the flow? Usually it is drains from the nearby locality, and of course from the pharma industry. So even at the hand, we have two rivers, but they are very much different. The strategy to model these rivers, these two different kinds of rivers, we use different strategies. For example, for the first river, the Chennai River, we will use hydrological model, the thing that I discussed in this lecture. But for the second river, for the Musi River, we may not need a hydrological model because it is not rain driven. The prime force is the releases from the reservoir. So we will just go with some hydraulic model, that too 1D model. So that is a kind of difference, meaning the modeler should understand a little bit regarding the characteristics of the flow in the catchment even before doing the model. So that is the thing. Coming to UK and India, I am not very sure about UK, but in India, few years back, we have a very well-defined rainy season. But these days, oh my God, even today, at some part, it is raining. And this year, we have found, I am from Odisha, a eastern state in India. And in that part, this year, we found something like 5 cyclones. And you know, all these cyclones and all these things, they are related to the water flow in the basin. So what I'm trying to say here is that, yes, if you look back into history, India typically has a typical, very well-defined rainy season. And so we expect the flow to be during that July, August, September, October. You may find many papers with these short notes like JASO, something like that, because these 4 months are considered typically to be the rainy season. So when you do the hydrological analysis, or when you do the hydrological modeling, or if I am looking for the data, I will be more interested for these 4 months, not other. But there are places, I know many places, not in India, outside. I was in US for 5 years. So in that place where I was living, there was no rainy season as such. So the rainfall was distributed throughout the year. So sometimes it may rain, it may be suddenly in January or in October. So what I'm trying to say here is looking back into the history of the events for that locality is extremely important. That way, a time series analysis, or as I said, the regional hydrology, that play a very major role in your analysis.
Can I ask a question in relation to this? That's about model calibration, because my understanding is of hydrological models that it's quite challenging to get both like high flow events and low flow events right in the calibration, and that must be quite challenging in a place like India, where you have heavy rainy seasons and things. I just wonder what your comment is on that.
Yes, you are very right. When as a modeler, when we try to calibrate, usually we study the floods. Therefore, there is a tendency in the modeler's mind that I will match the high flows. But as you said correctly, if you are planning to match the high flows, in all probability, your low flows will not be matched. And for example, the project that we are handling currently, this AMR flows, it is not for the floods. If there is a flood, everything will be flushed away. Of course, there will be other problems, but the most important thing here is to match the low flows. Yes, I agree completely with you. It is difficult to match both the low flows and the high flows. So depending on the objective of your work or exercise, you go ahead with whatever you want. And for this typical case, I believe personally, it should be the matching of the low flows, not the high flows.
And are they using they're just recording the level, right? And is that are they using a rating curve or something to convert to discharge, or is it something that you have to do?
There are different kinds of CWC sites. So usually they record the water level. From water level, they have already an established rating curve. So they convert that into discharge. But sometimes they also measure the sediment. That sediment measurement is not very frequent. The time gap is slightly more. Not 3 times a day. It is probably once in a month or something like that. And all CWC sites are not for sediment measurement. Only
are they trying to measure the suspended sediment or the?
Yes, suspended, only suspended, not bed load.
So I just give you some addition. So Josh, actually now many of the CW sites are, they have a telemetry connection, and so the online data is coming actually, and even that data also validated and calibrated. So there is one project called Hydrology project. So in that they have implemented it. Now the things are much better compared to earlier.
Yes. But many places they have kept as what they call something confidential or something like that.
Now the data policy, the new data policy actually they allow us online to
Yeah, for many places one can access.
Access.
But some locations are there.
And there are certain basins, different countries are sharing, so the basins which are shared by different countries. So other than that, I think much of the data is available online. But now, even if we ask, I think we will get the data. That's
things are so much better.
Yeah, thank you all very much. I think we'll have a quick comfort break of 5 minutes and carry on with the second session in 5 minutes.
Thank you very much.
Thank you very much, Pranab.
Thank you.